We will start at about 1 minute. Okay, today we'll cover section 8.4 on operations with radical expressions. We'll add and subtract radicals and multiply radicals. We'll have quiz 8 on Friday at about 8:40, 40 minutes past the hour. And to prepare for quiz 8, review solving equations with rational expressions. Those are from section 8.4. And then review solving applications with rational expressions from section 7.5. Okay, we'll start with adding and subtracting radicals from section 8.4. So we'll read this first paragraph. Like radicals can be combined by adding and subtracting. Simplified radicals are called like radicals if their indexes, variable parts, and radicands are the same. Like radicals may have different numerical coefficients. So one way to think about like radicals is similar to just thinking of like terms. For example, if you want to add 7x to 5x, you get a total of 12x. But with radicals, you have to make sure that the radicals are all as simplified as much as possible. And then you can tell if they are like radicals or not. This first example, 11 times the square root of 3 minus 7 times the square root of 3. The square root of 3 is as simplified as it can be. And the two terms are like radicals, so we can simplify by subtracting. 11 times the square root of 3 minus 7 times the square root of 3 simplifies to 4 times the square root of 3. In the same way that 11x minus 7x simplifies to 4x, that's how we simplify this difference. In the next example, we have 5 times the square root of x plus 3 times the square root of x minus the square root of x. Each of the radicals is identical, and the radical is simplified as much as possible. So we can combine by adding and subtracting. So we have 5 square root of x plus 3 square root of x minus 1 square root of x. Altogether, we have 7 times the square root of x. That's the simplified result. Okay, in the next example, 14y times the cubed root of 9x plus 11 times y times the cubed root of 9x. The radical cubed root of 9x is as simplified as possible. Notice also that outside of each of those two radicals is the factor y. So these terms are like terms, so we can combine them by adding. 14y times the cubed root of 9x plus 11y times the cubed root of 9x is a total of 25. y times the cubed root of 9x. In the next example, 13 times m times n times the fourth root of 7r minus 10 times m times n times the fourth root of 7r. These terms are like terms. The two radicals cannot be simplified any further. And so the variable parts outside of the radicals are identical and the radicands are identical. So we can combine by subtraction. So we have 13 of those minus 10 of the same kind. So we simplify that to 3 times m times n times the fourth root of 7r. Okay, a couple of more on this page. Here we have 19x to the second times the fifth root of 12y to the third minus 3x to the second times the fifth root of 12y to the third. The radical is as simplified as it can be, and they are identical, but also the variable parts on the outside have to be the same, and they are the same, so we can combine by subtraction. We have 19 of those terms minus 3 of the same kind of term, so altogether we just have 16x to the second times the fifth root of 12y to the third. Okay, the next one, negative 7a to the fourth times b to the fifth times the seventh root of 11c plus 10a to the fourth b to the fifth times the seventh root of 11c. The seventh root of 11c cannot be simplified any further, and both terms have that same radical, but also on the outside of the seventh root, each of the terms has b to the fifth and a to the fourth. So these can be combined by adding. We have negative 7 times that thing plus 10 times the same thing. So when we add them together, we get 3 times a to the fourth, b to the fifth, times the seventh root of 11c. Okay, we'll look at the next set of examples. In the next set of examples, they'll be a little bit more complicated, as you'll see. Okay, on the previous page, all of the radicals were already as simplified as they could be. But on this page, we're going to add and subtract radicals that are not all simplified. So this first example up here on the top left, 2 times the square root of 75 minus 9 times the square root of 48. The square root of 75 can be simplified further, and so can the square root of 48. So we have to simplify the radicals first, and then afterwards we have to determine if the terms can be added or subtracted. Okay, the largest factor of 75 that's a perfect square is 25. So 2 times the square root of 75 is the same as 2 times the square root of 25 times the square root of 3. And then minus 9 times, well, let's see, the largest factor of 48 that's a perfect square is 16. 16 times 3 is 48. So this is minus 9 times the square root of 16 times the square root of 3. And we'll start to use some shortcuts. By that I mean we won't write every single thing down. The square root of 25 is 5, and 2 times 5 is 10. So this term on the left simplifies to 10 times the square root of 3. And then minus 9 times the square root of 16. The square root of 16 is 4. And so minus 9 times 4 times the square root of 3 is just minus, well, 9 times 4 is 36. So minus 36 times the square root of 3. And the two radicals are identical, so we can combine them by subtraction. 10 times the square root of 3 minus 36 times the square root of 3 simplifies to negative 26 times the square root of 3. Okay, this isn't so bad if you can easily simplify the radicals. The next example, 2 times the square root of 5 plus 5 times the square root of 48 minus 3 times the square root of 20. Each of those square roots can be simplified further. The largest factor of 45, that's a perfect square, is 9. 9 times 5 is 45. So we will rewrite this as 2 times the square root of 9 times the square root of 5. And then the next term, the largest factor of 48, that's a perfect square, is 16. 16 times 3 is 48. So we will write this next term as 5 times the square root of 16 times the square root of 3. And then minus 3 times the square root of 20, the largest factor of 20 that's a perfect square is 4. 4 times 5 is 20. So we will write this as minus 3 times the square root of 4 times the square root of 5. And then starting over here on the left, the square root of 9 is 3. 2 times 3 is 6. So we get 6 times the square root of 5. And the middle term, 5 times the square root of 16. The square root of 16 is 4, and 5 times 4 is 20. So this is plus 20 times the square root of 3. And then on the right, the square root of 4 is 2, and minus 3 times 2 is minus 6. So minus 6 times the square root of 5. Okay, 2 of the radicals are like radicals, but the ones with the square root of 5 are unlike the middle term that has the square root of 3. But it turns out that 6 times the square root of 5 minus 6 times the square root of 5, those add up to 0. So the only term that's left is 20 times the square root of 3. Okay, the next example, 4 times the square root of 18xy to the second plus the square root of 8xy to the second minus 5y times the square root of 50x. Each of those square roots can be simplified further. So this one on the left, the largest factor of 18, that's a perfect square, is 9. 9 times 2 is 18. Y to the second is a perfect square, and x has to stay behind inside the square root. So we will rewrite this as 4 times the square root of 9y to the second multiplied by the square root of the remaining factors, 2 times x. In this process, you can always check to see if you're doing it correctly by multiplying. And just note that 2x times 9y to the second is 18xy to the second. Okay, in the next term, for the square root of 8xy to the second, the largest factor of 8 that's a perfect square is 4. 4 times 2 is 8. Y squared is a perfect square. So we will rewrite the middle term as the square root of 4y to the second times the square root of the remaining factors, 2 times x. And then the third term on the right, inside the radical, the square root of 50 can be simplified. The largest factor of 50 that's a perfect square is 25. 25 times 2 is 50. So we can rewrite this as minus 5y times the square root of 25 times the square root of 2x. Okay, we'll simplify the square roots of the perfect squares. The square root of 9y to the second is 3y, and 4 times 3y is 12y. So on this first term on the left, we have 12y times the square root of 2x. In the next term, the square root of 4y to the second simplifies to 2y. So we have 2y times the square root of 2x. And then over here, minus 5y times the square root of 25 times the square root of 2x. The square root of 25 is 5. So minus 5y times 5 times the square root of 2x is minus 25y times the square root of 2x. The simplified radicals are all identical, but also each of the terms has a factor of y on the outside of the radical. So these are like terms that can be combined by adding and subtracting. So 12 of those plus 2 of those, we're up to 14, and then 14 of those minus 25 of those is negative 11 times 2y times the square root of 2x. Okay, let's look at the next one. The next one involves cubed roots. Each one of those cubed roots can be simplified further. In the first one on the left, the largest factor of 16, that's a perfect square, or sorry, a perfect cube is 8. 2 to the third is 8, and 8 times 2 is 16. So we can rewrite this as the cubed root of 8 times the cubed root of 2m. Then for the next term, we have plus 5 times the cubed root of 54m. The largest factor of 54, that's a perfect cube, is 27. 27 times 2 is 54. So we can rewrite this middle term as plus 5 times the cubed root of 27 times the cubed root of 2m. And then the term on the right plus 2 times the cubed root of 40m. The largest factor of 40, that's a perfect cube, is 8. 8 times 5 is 40. So this one becomes plus 2 times the cubed root of 8 times the cubed root of 5m. Okay, so we'll simplify each of those further. The cubed root of 8 is 2, so we get 2 times the cubed root of 2m. And the next one, the cubed root of 27 is 3, and 5 times 3 is 15. So this middle term is plus 15 times the cubed root of 2m. And then the term on the right, the cubed root of 8 is 2. 2 times 2 is 4. So we have 4 times the cubed root of 5m. Only 2 of the terms can be combined by adding. The 2 terms on the left have identical radicals, cubed roots of 2m, but the term on the right is unlike the other 2. So this term on the right stands alone. When we combine the first 2, 2 of those plus 15 of the same, we have a total of 17 times the cubed root of 2m. And then over here on the right, 4 times the cubed root of 5m. This is as far as we can take it when simplifying, because the radicals are not like radicals. Okay, the next example, another bunch of cubed roots that we're adding and subtracting. Okay, the one on the left, the largest factor of 54, that's a perfect cube, is 27. 27 times 2 is 54. N to the third is a perfect cube because the exponent is a multiple of 3. So we'll rewrite this as the cubed root of 27 n to the third multiplied by the cubed root of 2. 2 is the only factor that remains behind. Okay, in the next middle term, we have plus 5n times the cubed root of 54. The largest factor of 54, that's a perfect cube, is 27. 27 times 2 is 54. So we rewrite this as 5n times the cubed root of 27 times the cubed root of 2. And then finally, the term on the right, minus 2 times the cubed root of 16n to the third. The largest factor of 16 that's a perfect cube is 8. N to the third is a perfect cube, so we will rewrite this as minus 2 times the cubed root of 8n to the third multiplied by the cubed root of the remaining factor, which is just 2. Okay, we'll simplify the cube roots of the perfect cubes. The cubed root of 27n to the third is 3n. So this term is 3n times the cubed root of 2. And then the middle term, the cubed root of 27 is 3, and 5n times 3 is 15n, so we get plus 15n times the cubed root of 2. And then the term on the right, the cubed root of 8n to the second simplifies to 2n. So minus 2 times 2n is minus 4n times the cubed root of 2. And all three terms are like terms. They have identical radicals, but each one also has a variable factor of n on the outside of the cubed roots. So we can combine these by adding and subtracting. So 3 of those plus 15 of the same, that gives us 18 n times the cubed root of 2. But then we're subtracting 4 n times the cubed root of 2. So altogether, we're just left with 14n times the cubed root of 2. Okay. That's all we're going to talk about regarding adding and subtracting. Now we will switch to multiplying with radicals. Okay, multiplying radicals. Well, we'll look at the product property of radicals. Let n be a positive integer. If the nth root of a and the nth root of b are real numbers, then the nth root of a times the nth root of b is equal to the nth root of a times b. Okay, in the first set of examples, I have a recommendation. Since in this first example, we're just multiplying 2 square roots, what I like to do is use the product property and write it as a single square root and multiply the 2 radicands, and then just focus on simplifying 1 square root. So if I apply the product property, I'm going to multiply 12x to the third y to the second by 3x to the fifth y, and that will give us, well, let's see, 12 times 3 is 36. X to the third times x to the fifth is x to the 8th. And then y to the 2nd times y is y to the 3rd. And then I'll just focus on simplifying this square root. 36 is a perfect square. X to the 8th is a perfect square. The largest factor of y to the 3rd that's a perfect square is y to the 2nd. Okay, so we'll rewrite this as the square root of the perfect square factors, 36 x to the 8th times y to the 2nd. And we'll multiply that by the square root of y. Y is the factor that has to stay behind inside the square root. And then we simplify the square root of the perfect square factors. The square root of 36 is 6. The square root of x to the 8th is x to the 4th. And the square root of y to the 2nd is y. And we multiply those by the square root of y. In the next example, we are multiplying two cube roots. But we'll do the same sort of thing that we did in the previous example. Since they are both cube roots, I can apply this product property of radicals. So this becomes the cubed root of whatever 4x times 2x to the 2nd is. 4x times 2x to the 2nd is 8x to the 3rd. And note that 8 is a perfect cube, and x to the 3rd is also a perfect cube. So we can write down what the simplified answer is immediately. The cube root of 8 is 2, and the cube root of x to the 3rd is x. So 2x is the simplified answer to that one. Okay, the next product, this time we have the 5th root of 2x to the 2nd y times the 5th root of 3x to the 3rd y to the 2nd. Okay, so we'll write it as a single 5th root and multiply these two radicands. 2 times 3 is 6. X to the 2nd times x to the 3rd is x to the 5th. Y times y to the 2nd is y to the 3rd. And we can simplify this. We cannot simplify the 5th root of 6, nor can we simplify the 5th root of y to the 3rd, but we can simplify the 5th root of x to the 5th, because x to the 5th is a perfect 5th power. So we can rewrite this as the 5th root of x to the 5th multiplied by the 5th root of 6y to the 3rd. And then the 5th root of x to the 5th is just x, so we multiply x times the 5th root of 6y to the 3rd. That's the simplified answer. Here, the next one is a product of square roots. The square root of 5x to the 7th times y to the 4th times the square root of 45x to the 9th y to the 3rd. So we will apply the product property of radicals and write it as a single square root. So inside the single square root, we have 5 times 45, which is 225. X to the 7th times x to the 9th is x to the 16th. We're adding the exponents when we multiply x to the 7th times x to the 9th. And then y to the 4th times y to the 3rd is y to the 7th. So we now just simplify this square root. 225 is a perfect square. 15 to the 2nd is 225. X to the 16th is a perfect square. The largest factor of y to the 7th that is a perfect square is y to the 6th. Okay, so we'll rewrite this as the square root of 225x to the 16th y to the 6th multiplied by the square root of y. Okay, then simplify the square root of the perfect square factors. The square root of 225 is 15. The square root of x to the 16th is x to the 8th, because the exponent 16 divided by 2 is 8. And the square root of y to the 6th is y to the 3rd. And so our final answer is 15x to the 8th y to the 3rd times the square root of y. Okay, in the next example, the fourth root of 2x to the 5th y to the 3rd times the fourth root of 8x to the 3rd y. So since they're both fourth roots and we're multiplying, we can write it as a single fourth root. And then inside the single fourth root, we have 2 times 8, which is 16, times x to the 5th times x to the 3rd, which is x to the 8th, times y to the 3rd times y, which is y to the 4th. And then we'll see if we can simplify the fourth root of 16x to the 8th y to the 4th. 16 is a perfect fourth power because 2 to the 4th is 16. X to the 8th is a perfect fourth power because the exponent 8 is a multiple of 4. 4 times 2 is 8. And y to the 4th is a perfect fourth power. So we can write the simplified answer right away. The fourth root of 16 is 2. The fourth root of x to the 8th is x to the 2nd because the exponent 8 divided by the index 4 is 2. And the fourth root of y to the 4th is y, which means y to the 1st. Okay, so that turned out to be pretty nice. Okay, the next one, the cubed root of 3x to the 5th y to the 3rd times the cubed root of 72x to the 7th y to the 6th. Since they are both cube roots, we can write it as a single cube root. So the cubed root, let's see, 3 times 72 is 216, and x to the 5th times x to the 7th is x to the 12th, because 5 plus 7 is 12. And then y to the 3rd times y to the 6th is y to the 9th. Okay, this one works out pretty nicely also because 216 is a perfect cube. 6 to the 3rd power is 216. X to the 12th is a perfect cube because the exponent 12 is a multiple of the index 3. And y to the 9th is also a perfect cube because it's a multiple of 3. So we can write the simplified result in the next step. The cube root of 216 is 6. The cube root of x to the 12th is x to the 4th because 12 divided by 3 is 4. And then times y to the 3rd because the exponent 9 divided by the index 3 is 3. Okay, we'll do a few more multiplying with radicals, but they will look a little bit different than these 6 examples that we just completed. Okay, so these next few examples involve radicals, but they look more like binomials. So if you just apply what you know about multiplying binomials to multiplying these kinds of expressions with radicals, then it'll work out nicely. Okay, so let's let's try this. We want to multiply the quantity square root of 7 plus 3 times the other quantity square root of 2 minus 5. So just like you would multiply two binomials, the square root of 7 times the square root of 2 is the square root of 14, because 7 times 2 is 14. And then we subtract the square root of 7 times 5. So we'll write that as minus 5 times the square root of 7. And then we add 3 times the square root of 2. 3 times the square root of 2. And finally, we subtract 3 times 5. So it's minus 15. Notice that this product that we got by expanding the product of those two terms, none of these terms can be combined because they're all different. They're not like terms. The square root of 14 cannot be simplified further, but it's unlike the square root of 7, and each of those is unlike the square root of 2. And 15, the minus 15 doesn't have a radical with it. So this is as simplified as this can get. Okay, in the next example, so this one, 4 times the square root of 3 plus the square root of 5, we're going to multiply that quantity by this quantity, which is the square root of 3 plus the square root of 5. So start on the left. 4 times the square root of 3 times the square root of 3 is 4 times the square root of 9, which is 4 times 3. I'll write down a little bit more detail on this one. We have time. 4 times the square root of 3 times the square root of 3. Think of that as 4 times the square root of 9, because 3 times 3 is 9. And then plus 4 times the square root of 3 times the square root of 5, which is 4 times the square root of 3 times 5, or 4 times the square root of 15. And then we shift over to this term, and we're going to add the square root of 5 times the square root of 3, which is the square root of 5 times 3, or the square root of 15. And then finally, we have plus the square root of 5 times the square root of 5, which is the square root of 25, because 5 times 5 is 25. And we can simplify the square root of 9 to 3. So this becomes 4 times 3. The two middle terms are like radicals, and they are already as simplified as they can be. So we can combine 4 times the square root of 15 plus 1 times the square root of 15 to get plus 5 times the square root of 15. And then plus the square root of 25 is plus 5. And we'll go ahead and write the completely simplified result in the next step. 4 times 3 is 12, and 12 plus 5 is 17. And then 17 plus 5 times the square root of 15 is the simplified result for that one. Okay, the next example, another pair of binomial-like expressions with radicals. So on this one, 3 times the square root of x plus the square root of y multiplied by 4 times the square root of x minus 6 times the square root of y. So let's write this as, okay, we're going to multiply 3 times the square root of x times 4 times the square root of x. 3 times 4 is 12. And the square root of x times the square root of x is the square root of x squared. Then we'll multiply 3 times the square root of x by negative 6 times the square root of y. So minus 3 times 6 is minus 18. And the square root of x times the square root of y is the square root of xy. And then we multiply the square root of y times 4 times the square root of y. So we're going to write plus 4 times the square root of xy. And then the final term in the multiplication minus the square root of y times 6 times the square root of y. So this is minus 6 times the square root of y squared. Okay, this is working out pretty nicely. The square root of x squared is just x. So this term on the left is just 12x. The two middle terms are like radicals, so we can combine those. Minus 18 times the square root of xy plus 4 times the square root of xy is equivalent to minus 14 times the square root of xy. And then the term on the right, the square root of y squared is y, so the term on the right is minus 6y. And so this is the simplified result of that one. Okay, a couple of more examples. 6 times the cube root of x minus 5 times the cube root of x plus 2. First, we multiply 6 times the cube root of x times the cube root of x. And we get 6 times the cube root of x times x, or the 6 times the cube root of x squared. And then we're going to add 6 times the cube root of x times 2. 6 times 2 is 12, so this is plus 12 times the cube root of x. And then we're going to subtract 5 times the cube root of x. And finally, we are going to subtract 5 times 2, which is minus 10. On the left, the cube root of x squared cannot be simplified any further. So we'll just write 6 times the cube root of x to the second. The two middle terms can be combined because the radicals are like radicals. First note that the cube root of x can't be simplified any further. So we can go ahead and subtract these, we can subtract this one from that one. 12 cubed roots of x minus 5 times the cube root of x simplifies to plus 7 times the cube root of x. And then we have minus 10. That's the simplified result of that one. Okay, the last one on this page. This one we're multiplying 5 times the 4th root of x to the 3rd minus 7 times the 4th root of x minus 4. We start by multiplying 5 times the 4th root of x to the 3rd by the 4th root of x. And so that's 5 times the 4th root of x to the 4th, because x to the 3rd times x is x to the 4th. Then we're going to subtract 5 times the 4th root of x to the 3rd by times 4. So since 5 times 4 is 20, this is going to be minus 20 times the 4th root of x to the 3rd. And then we're going to subtract 7 times the 4th root of x. And finally, negative 7 times negative 4 is positive 28. So on the right, we're going to add 28. Okay, there is one more thing that can be simplified. The 4th root of x to the 4th is just x. So this term on the left is just 5x. And the two middle terms are not like terms, so they cannot be combined. They are both fourth roots, but inside each of those, we have different terms. So we can't combine the middle terms this time. So it's 5x minus 20 times the fourth root of x to the third minus 7 times the fourth root of x and plus 28. Okay, we'll review a couple of application problems in the remaining time. So this will be this might help review for Friday's quiz. So this one says, this is from section 7.5. A carpenter can build a patio cover in 6 hours. His partner takes 8 hours to build the same cover. And based on that information, we can find how long it would take them working together to build the patio. Okay, so there are 3 scenarios to consider. The carpenter works by himself, his partner works by himself, and then they work together. So I'll just label the 3 categories: the carpenter working by himself, and the partner working by himself, and then they work together. Okay, this is a work problem, so equations have the form rate times time equals 1. Okay, so we're told that when the carpenter works by himself, he can build the patio cover in 6 hours. So the carpenter works at his rate, and in 6 hours, he can build 1 patio cover. So we have rate times time equals 1. The partner takes 8 hours by himself. So the partner works at a certain rate. I'll label that R sub P. And in 8 hours, he can build 1 patio cover. And we can use that information to determine how long it takes them when they work together. So the carpenter's rate plus the partner's rate times, I'll call it T, equals 1. T represents the amount of time it takes them working together to build the patio cover. Okay, so we'll solve each of those 3 equations for the rates. The carpenter's rate is 1/6, which means he can build 1/6 of the patio cover per hour. The partner's rate is 1/8. That means that in 1 hour, he can build 1/8 of the patio cover. And then we divide both sides of this equation by T. So the carpenter's rate plus the partner's rate is 1/T. And then in the next step, we replace the carpenter's rate with 1/6. We're adding that to the partner's rate, which is 1/8. And the carpenter's rate plus the partner's rate is equal to 1/T. And we're going to solve this for T. So the least common denominator is just 24T. And we'll multiply every term on both sides by 24T. So 24T over 1 times 1/6 plus 24T over 1 times 1/8 equals 24T over 1 times 1/T. Okay, we'll simplify each of those products. This is just 24t divided by 6, which is 4t. And then plus 24t divided by 8 is plus 3t. And then 24t divided by t is 24. So we get 7t equals 24, and t equals 24 over t. Hey, so that's all we have time for today. Remember the quiz 8 on Friday. I'll send an email about that between now and then, just to make sure you're prepared. That's all for now. I do that right. Oops. 4, 7. We'll start in about 1 minute. Today we will cover the rest of section 8.4 on operations with radical expressions, and then section 8.5 we will discuss how to divide with radicals and rationalize denominators. We'll have a quiz 8 on Friday at about 40 minutes past the hour. And to prepare for quiz 8, you can review solving equations with rational expressions from section 7.4, and also review solving applications with rational expressions from section 7.5. Okay, we'll get started with the rest of section 8.4. Last time we talked about how to add and subtract radicals. Today we'll talk about how to divide or how to multiply with radicals. So the product property of radicals, if we let n be a positive integer, if the nth root of a and the nth root of b are real numbers, then if we multiply the nth root of a by the nth root of b, we can write it as the nth root of a times b. Okay, so generally, if we're multiplying two radicals with the same index, my advice is to write it as a single radical and multiply the radicands. So on this one, the square root of 12x to the third y to the second times the square root of 3x to the fifth y. What I suggest is apply the product property of radicals, write it as a single square root, and we'll multiply the two radicands. 12 times 3 is 36. X to the third times x to the fifth is x to the eighth. And y to the second times y is y to the third. And then afterwards, focus on simplifying this single square root. 36 is a perfect square. X to the eighth is a perfect square because the exponent 8 is a multiple of the index 2. And the largest factor of y to the third that's a perfect square is y to the second. So we'll rewrite this with the perfect square factors farther to the left, the square root of 36, x to the eighth, y to the second, multiplied by the square root of the remaining factor y. You can always verify that you're doing this correctly just by multiplying the radicands. Okay, in the next step, we can simplify the square root of the perfect square factors. The square root of 36 is 6. The square root of x to the eighth is x to the fourth, because the exponent 8 divided by the index 2 is 4. And the square root of y to the second is y. And we multiply 6x to the fourth y times the square root of y. This is the simplified answer. The next product involves cubed roots. The cubed root of 4x times the cubed root of 2x to the second. So we'll write it as a single cubed root and multiply the radicands. 4x times 2x to the second is 8x to the third. And note that 8 is a perfect cube, and so is x to the third. X to the third is a perfect cube because the exponent 3 is a multiple of the index 3. So in the next step, we can write the completely simplified term. The cubed root of 8 is 2. The cubed root of x to the third is x. Okay, the next one involves multiplying two fifth roots. The fifth root of 2x to the second y times the fifth root of 3x to the third y to the second. So let's write it as a single fifth root. Inside the single fifth root, 2 times 3 is 6. X to the second times x to the third is x to the fifth. We're adding the exponents when we multiply the terms with the same base. And then y times y to the second is y to the third. The only factor that is a perfect fifth power is x to the fifth. So we can rewrite this as the fifth root of x to the fifth multiplied by the fifth root of the factors that have to stay behind. So 6 times y to the third. And then we simplify the fifth root of x to the fifth. That simplifies to x. And so we multiply x times the fifth root of 6y to the third. That's the simplified answer. In the next product, the square root of 5x to the seventh y to the fourth times the square root of 45x to the ninth y to the third. Since we're multiplying two square roots, we can write it as a single square root. And 5 times 45 is 225. X to the seventh times x to the ninth is x to the 16th. And y to the fourth times y to the third is y to the seventh. And now we'll just focus on simplifying this single square root. 225 is a perfect square. 15 to the second is 225. X to the 16th is a perfect square because 16 is a multiple of 2. The largest factor of y to the seventh that is a perfect square is y to the sixth. And y to the sixth times y is y to the seventh. So we'll rewrite this as the square root of 225 x to the 16th y to the sixth multiplied by the square root of y. The square root of 225 is 15. The square root of x to the 16th is x to the 8th. The square root of y to the 6th is y to the 3rd. So our final answer is 15 times x to the 8th times y to the 3rd times the square root of y. Okay, 2 more examples on this page. On the lower left, the fourth root of 2x to the 5th y to the 3rd times the fourth root of 8x to the 3rd y. Since we're multiplying two fourth roots, we can write it as a single fourth root. And so we'll multiply the two radicands above. 2 times 8 is 16. X to the 5th times x to the 3rd is x to the 8th. And y to the 3rd times y is y to the 4th. Each of the factors on the inside of this fourth root are perfect fourth powers. 16 is 2 to the 4th. X to the 8th is a perfect fourth power because the exponent 8 is a multiple of 4. And y to the 4th is obviously a perfect fourth power. So the next step is the completely simplified answer. The fourth root of 16 is 2. The fourth root of x to the 8th is x to the 2nd. And the fourth root of y to the 4th is y, which means y to the 1st. Okay, the next example, this time we're multiplying two cubed roots. So we'll write it as a single cubed root. 3 times 72 is 216. X to the 5th times x to the 7th is x to the 12th. And y to the 3rd times y to the 6th is y to the 9th. Okay, this one works out as nicely as the previous one. 216 is a perfect cube because 6 to the 3rd power is 216. X to the 12th is a perfect cube or perfect 3rd power because 12 is a multiple of 3. And y to the 9th is a perfect cube also because 9 is a multiple of 3. So our next answer is the completely simplified answer. The cube root of 216 is 6. The cube root of x to the 12th is x to the 4th because 12 divided by 3 is 4. And times y to the 3rd because 9 divided by 3 is 3. And we'll do some more multiplying involving radicals. They'll look a little different than these 6 examples that we just did. Okay, these are binomial-like factors. So this first one up here, the square root of 7 plus 3 times the square root of 2 minus 5. So we'll just multiply those like we would multiply binomials. The square root of 7 times the square root of 2 is the square root of 14 because 7 times 2 is 14. And then minus the square root of 7 times 5. So we write it as minus 5 times the square root of 7. And then we're going to add 3 times the square root of 2, which is plus 3 times the square root of 2. And finally, we subtract 3 times 5 is minus 15. None of these terms are like the others, so we can't simplify any further than this. Each of the 3 radicals are different. Each one is as simplified as possible, but they're all unlike radicals. And then a constant can never be combined with a radical. So this is the simplified answer. Okay, in the next example, 4 times the square root of 3 plus the square root of 5 times the square root of 3 plus the square root of 5. So first multiply 4 times the square root of 3 times the square root of 3. So we'll write it as 4 times the square root of 9 because the square root of 3 times the square root of 3 is the square root of 9. Then we're going to add that to 4 times the square root of 3 times the square root of 5, which is plus 4 times the square root of 15. That's because the square root of 3 times the square root of 5 is the square root of 3 times 5. Okay, then we multiply the square root of 5 times the square root of 3. So this is plus the square root of 15. And then finally, we're going to add the square root of 5 times the square root of 5, which is the square root of 25. Okay, we can simplify a little bit. The square root of 9 is 3, so this becomes 4 times 3. The 2 middle terms are like terms, or they have like radicals. The radicals are the square roots are already as simplified as they can be on those 2 middle terms. So 4 times the square root of 15 plus 1 times the square root of 15 is just plus 5 times the square root of 15. And then the square root of 25 is 5. And in the next step, we'll just write the completely simplified result. 4 times 3 is 12, and 12 plus 5 is 17. So we have 17, and that's added to 5 times the square root of 15. This is as simplified as it can get. Okay, in the next example, 3 times the square root of x plus the square root of y times 4 times the square root of x times minus 6 times the square root of y. Okay, so first multiply 3 times the square root of x times 4 times the square root of x. So 3 times 4 is 12, and the square root of x times the square root of x is the square root of x squared. So in our first step, this is what we can write when we multiply those first terms. Then we're going to subtract 3 times the square root of x times 6 times the square root of y. So we're going to subtract 18 times the square root of x times y. Then we're going to add the square root of y times 4 times the square root of x. So we write that as plus 4 times the square root of xy. And then we're going to subtract the square root of y times 6 times the square root of y, which is minus 6 times the square root of y to the second. Okay, we can simplify further. The square root of x squared is x. So this the 12 times the square root of x squared simplifies to 12x. The two middle terms are like terms. Each of the radicals is simplified and each one is identical to the other. So minus 18 times the square root of xy plus 4 times the square root of xy. That simplifies to minus 14 times the square root of xy. And then finally, minus 6 times the square root of y squared simplifies to minus 6 times y. So this is the simplified result. Okay, a couple of more. 6 times the cubed root of x minus 5 times the cubed root of x plus 2. First, 6 times the cubed root of x times the cubed root of x. That's 6 times the cubed root of x squared. Then we're going to add 6 times the cubed root of x times 2, or plus 12 times the cubed root of x. And then minus 5 times the cubed root of x is minus 5 times the cubed root of x. And finally, minus 5 times 2 is just minus 10. 6 times the cubed root of x to the second. This cannot be simplified any further. The two middle terms are like terms. They have the radicals are already simplified and they are identical. So we can combine those by subtraction. And then the minus 10 stands alone by itself. So our simplified answer is 6 times the cubed root of x squared. And when we combine the middle terms by subtraction, we get plus 7 times the cubed root of x, and then minus 10. Okay, one more example, and then after this final example, we'll talk about division involving radicals and rationalizing denominators. Okay, so 5 times the 4th root of x to the third times the 4th root of x. That's 5 times the 4th root of x to the 4th. For this x to the 4th, we got that by multiplying x to the third times x. And then we're going to subtract 5 times the 4th root of x to the third times 4. So that's minus 20 times the 4th root of x to the third. And then we're going to subtract 7 times the 4th root of x. So that's just minus 7 times the 4th root of x. And then since -7 times -4 is positive 28, we're going to add 28. We can only simplify one more thing. The fourth root of x to the fourth simplifies to x because the exponent 4 divided by the index 4 is 1. So this becomes 5x. Note that the two middle terms are not like terms. This one involves the fourth root of x to the third, but that is different than this one that has the fourth root of x. So none of those remaining terms can be combined. So the simplified product is 5x minus 20 times the fourth root of x to the third minus 7 times the fourth root of x plus 28. That's as simplified as it can get. Okay, what we'll do the next 30 minutes or so is going to be more challenging. Okay, we're going to divide with radicals and also rationalize denominators. So the quotient property of radicals, let n be a positive integer. And if the nth root of a and the nth root of b are real numbers, and b is not equal to 0, then the nth root of a divided by the nth root of b is equal to the nth root of a divided by b. We've already seen this quotient property of radicals in section 8.2. The quotient property of radicals was discussed, but in those examples, the radical in the denominator was easy to simplify. So here is an example like the ones that we saw in section 8.2. Simplify the square root of 18x to the fifth divided by 49y to the fourth. Okay, so we can rewrite this as a quotient of square roots. In the numerator, we have the square root of 18x to the fifth. And in the denominator, we have the square root of 49y to the fourth. And in the denominator, we have the square root of perfect squares. The square root of 49 is just 7, and the square root of y to the fourth is y to the second. So the denominator simplifies nicely to 7y to the second. And then there's more to do in the numerator. The largest factor of 18 that's a perfect square is 9, and the largest factor of x to the fifth that's a perfect square is x to the fourth. So we can rewrite the numerator as the square root of 9x to the fourth times the square root of 2x. And then we simplify the square root of 9x to the fourth. That simplifies to 3x to the second. So in the numerator, we have 3x to the second times the square root of 2x. And then in the denominator, we just have 7y to the second. Okay, so that was pretty straightforward. In this section, 8.5, it's going to be more complicated. So we'll start with this paragraph. In this section, it will be more complicated. If after simplifying a quotient of radicals, there is still a radical in the denominator, then further simplifying is necessary. So the completely simplified radical expression will not have a radical in the denominator. Rationalizing the denominator is the name of this process of eliminating a radical in a denominator. So by rationalizing the denominator, that means that in the end, we want the denominator to be a rational number. A rational number is a number that can be written as an ordinary fraction. So I'll explain in a number of examples how to rationalize denominators when necessary. Okay, so in this first example, the square root of 5 divided by the square root of 7. In this case, the denominator is not a rational number, it's an irrational number. The square root of 7 cannot be written as an ordinary fraction where both the numerator and denominator are integers. But we need to be able to find a number that's equal to this number in value, but whose denominator does not have a square root in it. Okay, so what we do, if the denominator has a square root in it that's already simplified, the square root of 7 is as simplified as it can be. Since it's a square root of 7, we ask this question. What would I have to multiply by 7 to get a perfect square? Well, if I multiply 7 times 7, I get 49, and 49 is a perfect square. So that is an adequate answer to that question. So that informs what we do in the next step. We're going to multiply this by 1 in the form the square root of 7 divided by the square root of 7. Okay, you'll agree that the square root of 7 divided by the square root of 7 equals 1. And anytime you multiply a number by 1, you're not changing its value. But the intent here is to change the form so that the denominator is a rational number. So now we just multiply the two quotients. In the numerator, the square root of 5 times the square root of 7 is the square root of 35. And in the denominator, the square root of 7 times the square root of 7 is the square root of 49, but the square root of 49 is 7. Now the denominator is a rational number. 7 can be written as an ordinary fraction, 7 over 1. So we succeeded in rationalizing the denominator. But the value of this number, the square root of 35 divided by 7, is the exact same value as the square root of 5 divided by the square root of 7. Okay, so it's this kind of thing that we're going to do when rationalizing denominators. In the next example, we have the cubed root of 5 divided by the cubed root of 7. Well, cube roots are not the same as square roots. But the denominator, the cubed root of 7, is already simplified as a cubed root anyway. So since it's a cubed root, this time we ask a different question. This time we ask, what would I have to multiply by 7 to get a perfect cube? Well, think of 7 as 7 to the first. And if I multiply 7 to the first times 7 to the second, I get 7 to the third, and 7 to the third is a perfect cube. 7 to the third is just 343. Okay, but what I have to multiply by 7 to get a perfect cube is 49. So that informs what we do next. We're going to multiply by 1 in the form the cubed root of 49 divided by the cubed root of 49. So once again, we're just multiplying by 1. The cubed root of 49 divided by the cubed root of 49 is 1. We're just multiplying by 1. So in the numerator, we multiply these two numerators. The cubed root of 5 times the cubed root of 59 is the cubed root of 245. And in the denominator, the cubed root of 7 times the cubed root of 49. Well, you can think of it in a couple of ways. Maybe the easiest way is to think of this as the cubed root of 7 to the third. Or you could multiply 7 times 49, and it's the cubed root of 343. But the cubed root of 343 simplifies to 7. And now the denominator is a rational number. But this number, the cubed root of 245 over 7, has the same exact value as the cubed root of 5 divided by the cubed root of 7. Okay, so we can start to pick up the pace a little bit. On this one, 4 divided by the cubed root of 25. 25 is 5 to the second. So if you multiply 5 to the second times 5, you get 5 to the third. So in this one, we're going to multiply by 1 in the form the cubed root of 5 divided by the cubed root of 5. And then in the product, we multiply the numerators. 4 times the cubed root of 5 divided by the cubed root of 125, because 25 times 5 is 125. But the denominator will simplify to 5. So our final simplified answer is 4 times the cubed root of 5 divided by 5. We now have a rational number in the denominator. Okay, the next one, 11 divided by the cubed root of, sorry, not the cubed root, 11 divided by the fourth root of 9. 9 can be thought of as 3 to the second. So if I multiply 3 to the second times 3 to the second, I get 3 to the fourth, and 3 to the fourth is a perfect fourth power. So we multiply the numerator by the fourth root of 3 to the second, but 3 to the second is just 9. So the fourth root of 9 divided by the fourth root of 9. Then we multiply those terms. In the numerator, we get 11 times the fourth root of 9. In the denominator, the fourth root of 9 times the fourth root of 9 is the fourth root of 81. But 81 is a perfect fourth power, so the denominator simplifies to 3. So now we have a rational denominator. Okay, in the next example, simplify the square root of 7 over 20x. It's not required, but you can rewrite this as the square root of 7 over the square root of 20x. It might be easier to think about what's going on if you do it that way. So since there's a square root in the denominator, and in the end, we don't want a square root in the denominator, we ask, what would I have to multiply by 20x to get a perfect square? Start with the factor 20. If you multiply 20 times 5, you get 100, and 100 is a perfect square. And if you multiply x by x, you get x squared, which is a perfect square. So this analysis indicates that we should multiply by 1 in the form the square root of 5x divided by the square root of 5x. And in the numerator, the square root of 7 times the square root of 5x is the square root of 35x. And in the denominator, the square root of 20x times the square root of 5x is the square root of 100x to the second. But now we can simplify the denominator so that there's no longer a square root in the denominator. The final result is the square root of 35x. So we want to make sure the x is inside the square root in the numerator. And then in the denominator, the square root of 100 is 10, and the square root of x to the second is x. We no longer have a square root in the denominator. Okay, one more on this page. The fifth root of 13 divided by the fifth root of 16x to the third. We want to get rid of the fifth root in the denominator, so we have to figure out what form 1 takes this time. 16 is 2 to the fourth, so if you multiply 2 to the fourth times 2, you get 2 to the fifth. 2 to the fifth is a perfect fourth power. Sorry, a perfect. Let me back up. 2 to the fourth times 2 is 2 to the fifth, which is a perfect fifth power. And if you multiply x to the third times x to the second, you get x to the fifth, which is a perfect fifth power. So the form that 1 takes this time is the fifth root of 2 times x to the second divided by the fifth root of 2 times x to the second. And then in the numerator, the fifth root of 13 times the fifth root of 2x to the second is the fifth root of 26x to the second. And in the denominator, the fifth root of 16x to the third times the fifth root of 2x to the second is the fifth root of 32x to the fifth. But the denominator can be simplified so that there's no longer a fifth root in the denominator. So I guess I'll write it down here. The simplified result, the fifth root of 26x to the second in the numerator. That can't be simplified any further. But in the denominator, the fifth root of 32 is 2, because 2 to the fifth is 32, and the fifth root of x to the fifth is just x. So now we no longer have a fifth root in the denominator. We succeeded in rationalizing the denominator. Okay, we'll do one more example like these, and then we'll look at some other types of examples. So let's take a look at this one. Simplify the cubed root of 125 divided by the cubed root of 16y. Well, there's more than one way to go about this, but in the denominator, if we were to multiply 16 times 4, we would get 64. 64 is a perfect cube. And if we were to multiply y times y to the second, we get y to the third, which is also a perfect cube. So if we multiply by 1 in the form the cubed root of 4y to the second divided by the cubed root of 4y to the second, this will get us where we want to go. But notice that the cubed root of 125 in the numerators simplifies to 5 because 125 is a perfect cube. So it's to our advantage to notice that. Simplify the cubed root of 125 to 5, and then we're multiplying 5 times the cubed root of 4y to the second. If you didn't notice that, we could have written the cubed root of 500 y to the second. And we could still make it work, but it would be more work in the long run. Okay, in the denominator, the cubed root of 16y times the cubed root of 4y to the second is the cubed root of 64, because 4 times 16 is 64 times y to the third. And the denominator can be simplified so that there's no longer a cubed root in it. So the numerator is 5 times the cubed root of 4y to the second. And the cubed root of 64 is 4, and the cubed root of y to the third is y. So we rationalize the denominator. Okay, the next few examples have a little bit different feel to them, but we're still going to just multiply by 1. Okay, on this one we have 3 divided by 5 minus the square root of 3. So since the denominator is 5 minus the square root of 3, we're going to multiply by 1 so that both the numerator and denominator have what we call the conjugate of the denominator. The conjugate of 5 minus the square root of 3 is 5 plus the square root of 3. So we divide by 1 in the form 5 plus the square root of 3 divided by 5 plus the square root of 3. So now we just multiply. In the numerator, 3 times 5 is 15, and plus 3 times the square root of 3 is plus 3 times the square root of 3. In the denominator, 5 times 5 is 25, and then plus 5 times the square root of 3, and then minus the square root of 3 times 5, which is minus 5 times the square root of 3. And then finally, we have minus the square root of 3 times the square root of 3, which is minus the square root of 9, or 3. Okay, you'll be able to see why multiplying the numerator and the denominator by the conjugate of the denominator is what we want to do, because the radicals will completely disappear in the denominator. In the numerator, we have 15 plus 3 times the square root of 3. In the denominator, we can combine 25 minus 3, which is 22. But plus 5 times the square root of 3 minus 5 times the square root of 3, these cancel each other out, so that we're just left with 22 in the denominator. And so the denominator has been rationalized. Okay, in the next example, 29 divided by 8 plus the square root of 7. The square root of 7 is not a rational number. So in the end, we want a number that has the same value as this, but with a rational denominator. So once again, we multiply the numerator and denominator by the conjugate of the denominator. The conjugate of 8 plus the square root of 7 is 8 minus the square root of 7. So we multiply the numerator and denominator by 8 minus the square root of 7. And after we do this, the square roots from the denominator will be eliminated. So 29 times 8 is 232, and then minus 29 times the square root of 7 in the numerator. In the denominator, 8 times 8 is 64, and then minus 8 times the square root of 7, and then plus 8 times the square root of 7. Those are canceling each other out. And then we have minus the square root of 7 times the square root of 7, which is just minus 7. And then the simplified result in the numerator, 232 minus 29 times the square root of 7. And in the denominator, we're just left with 64 minus 7, which is 57. So that's the simplified result. Okay, let's try this one. 2 divided by the square root of 5 minus the square root of 3. This time we have 2 square roots in the denominator, but we still do the same thing that we did in the previous 2 examples. We're going to multiply the numerator and denominator by the conjugate of the denominator. The conjugate of the square root of 5 minus the square root of 3 is the square root of 5 plus the square root of 3. So we multiply the numerator and denominator by the square root of 5 plus the square root of 3. In the numerator, we get 2 times the square root of 5 plus 2 times the square root of 3. In the denominator, the square root of 5 times the square root of 5 is the square root of 25. That simplifies to 5. Then we have plus the square root of 5 times the square root of 3, which is plus the square root of 15. And then we have minus the square root of 3 times the square root of 5, which is minus the square root of 15. And then minus the square root of 3 times the square root of 3 is minus the square root of 9. And you can see what's going to happen. In the numerator, the radicals in the numerator are not like radicals, so they can't be combined. 2 times the square root of 5 plus 2 times the square root of 3. In the denominator, the square root of 25 is 5. The plus square root of 15 minus the square root of 15, those add up to 0. And then minus 3, because the square root of 9 is 3. The denominator is going to be 2. 5 minus 3 is 2. And notice that every term in the numerator has a factor of 2. So if we divide every term in the numerator by 2, our simplified answer is going to be the square root of 5 plus the square root of 3. Okay, I'm going to skip this example for now, but I'll just mention you can multiply the numerator and denominator by 3 minus the square root of x. I want to look at 1 or 2 in the remaining 3 or 4 minutes that are a little, they're not really that difficult, but I just want you to see them. So this one up here, we want to rationalize the denominator. The denominator is the square root of x minus the square root of x. So just like we did before, we're going to multiply the numerator and denominator by the conjugate of the denominator. So the conjugate is the square root of x plus the square root of y. So we multiply the numerator and the denominator by the square root of x plus the square root of y. And then multiply the 2 numerators. X times the square root of x is x times the square root of x. And then plus x times the square root of y is plus x times the square root of y. And then plus y times the square root of x plus y times the square root of x. And finally, plus y times the square root of y plus y times the square root of y. In the denominator, the square root of x times the square root of x is the square root of x squared. And then plus the square root of x times the square root of y, which is plus the square root of xy. And then minus the square root of y times the square root of x is minus the square root of xy. And then finally, minus the square root of y times the square root of y is minus the square root of y to the second. The 2 middle terms cancel each other out, so those are going to disappear. And the square root of x squared simplifies to x, and the square root of y squared simplifies to y. So the denominator is going to simplify to x minus y. But in the numerator, none of the terms are like terms. So we have to list them all separately. X times the square root of x plus x times the square root of y plus y times the square root of x plus y times the square root of y. Okay, so we're about out of time for today. On Friday, we'll look at section 8.6 and 8.8, but also be prepared for the quiz. Just as a reminder for Friday's quiz, I'm going to email the PDF, and you'll have 20 minutes to finish it, and then email the finished quiz back by replying to the email that I sent. But you can review solving equations with rational expressions and also review solving applications with rational expressions. Those are from 7.4 and 7.5. So that's all for today.